would say good morning to the guys in the stream too. Once. Okay.
Professor,
Yeah.
um,
Yes,
I
please.
have for the second session, so after 1 hour and 30, I have an appointment with the how you say prefecture. It's
Mm-hmm.
like for my visa, so I need to go if
Mm.
it doesn't mind with you
Okay.
after the first class. And the second one, I will review it
Mm-hmm.
on
Yeah.
the stream.
It is okay. So um, I will record the lecture, and I think I should link the videos into the Moodle um,
Well, thank you very
course,
much.
and you have the chance to watch it later. Okay?
Thank you very much.
Mm-hmm. You're welcome. Good, then let's go on with a little bit of the programming language Kotlin. We've already learned or saw already lots of new fantastic things. How Kotlin is making programming much easier for us to use if we are already experienced in programming and know what the problems in programming really are. We have a feeling for how Kotlin is helping us in that way. So if we don't have the background in how to program with null pointers, how to program with exceptions and so on, and how to write lots of statements and lots of conditions and control flow and so on, then we really know how what's the fertile that Kotlin is giving us here in this in in this condition. So what we did last week is we came up until the nearly the end of our basics. I think, yeah, it was the end. We talked about type conversions, type casting, and automatic or implicit type extension or typecast, but we have the possibility to explicitly cast every type of the basic types into every other type. This is realized through the methods to and then the simple types here for every type. Okay, other things where we have characters, and this time they are not really numbers. You know this from other programming languages. A character is simply a byte-sized number type, so it's a integer type. This is not here the case. They are not anymore compatible with the numbers, but we can convert. We have a two-character method, so we can do conversion, but everything type. And another thing, we will start over with object-oriented programming today. So we go into the really interesting things, into classes and objects. And there is lots of more stuff done here in Kotlin, so it will stay interesting, I think, for everybody. So this is one case, and therefore we only have objects. You see the big capital letter and starts for every type. So integer, double, as we have seen in our examples, all have a capital letter, and this is a hint to that this type name is in fact a class name. So there is never no more primitive types here. We don't have primitive types. All types are object types in this way. Okay, so we have characters, okay, Boolean, this is what we had. We talked about arrays as well. We have methods like get with an index or set with an index, and what we have behind those methods, those are operator compatible methods, and the operator with the brackets is the index access operator, what is behind this here. So, and we have a size. This is normal, so you know every array object in Java as well does know its size, and we have the possibility to access with the index. Different library functions we have seen already. I have the last example here. So how create an integer array? We have the function int array. We can give a size, then we get a array of size 5, and as well as the initialization of those values in the array, those 5 values. It will be called with a lambda expression. The one and only parameter available in this lambda is the index. So those 5 elements are indexed from 0 to 4, and this value here, this parameter here, its default, and its name is it, is here the index value for each element. This code, this piece of code is called, and the element is set to this value. So index value plus 1 is the outcome here. Every element now gets a value. The element with the index 0 gets the value 1, and the element with the index 4 gets the value 5. If we print this array with maybe a for each, then we get printed out every element, and running this code gives us the numbers 1, 2, 3, 4, 5. You see here in this example I did very much with lambda expressions. Lambda is a core thing in Kotlin. That's why we almost everywhere find it. And this is a constructor constructing a array, and this constructor has 2 parameters. Normally this one is the constructor call, and if the last parameter in a parameter list is a lambda expression like this one here, we can leave it out and make it like this. So this is it looks like a function body defined for this construction of the array now. And the same approach here. This is a method which has only a for loop inside, going over all array indices here, doing the same like the this constructor here, going over all elements in the array, giving us the index. The only parameter for this lambda expression is the index number I, and not the index number, is the value actually on the position going from 0 to 4. So we get the value in the array positions and can print it out. This function body here is the body of a for loop, and the value we can access is this variable. I think we do it. I don't know if it's today or if it's next week, if we come so far that we talk about lambda expressions in this case. Yeah. Okay. So that is this piece of code here explained, that you can read it. So you might know it because there's the name for each, so you know it must be some loop which is iterating over each element in this array, and we can print this here. And this it is, if a lambda has only one parameter, it's always called it. So it's simple for us to write those small lambda expressions. Other loops we could do also with a lambda. We could do a while loop or other counting loops with lambda. If we call something times, and let's say 5 times. Moment. It's called times. No. Repeat. Sorry. Repeat 5 times, and we could print. Then we get the number. This is a for loop as well. we repeat 5 times, so the number of times to repeat is known, and we get the value here as well. So 1 to 5 and then 0 to 4, maybe a print line in between. It's the same approach, but we do not iterate over the array. We have just a loop, and this here is the loop body. We get from the for loop, we get the counter value. Here is always called it. You know, if you write a for loop, you would start with maybe the integer called I. So typical, we call the integer value I, and if we have a other loop inside the first loop, we name the next loop variable j, so we could have I or j or both. And here we have in this lambda approach, we have it as only parameter. It's as well a counting loop, counting 5 times. Good. So far, some examples to come back in, mainly with those arrays. We have the array of functions. We can write arrays simply with array of, or maybe another example here. Do this way and make array of. And this array of, we have a variable arguments list which we can put in here, but this array of should be defined in integer so that we can work with it. We need a type here, and then just have variable arguments, so we can write 1, 2, 3, 4, 5, have the same array of these 5 values. It's the same as before. And for this array of int, we have an special method which creates the int array of is the same. So in case of an array of int, we can write int array of. For the simple or primitive types, we always have those overloads and can use it. This is the only difference. In this way, we have the possibility to have a empty array. This array now is empty, so it does not give anything out. Can't give anything out because it's a empty array, and the size is 0. It's 0. That's right. If we use int array as a constructor, we have always to give a value, so this is a other 0-sized array with size 0. Okay? So int array is the special array int. But here we have to give something back. In this case, if we use array int, we have to give something back. It is size 0, so we get the 0. It's the same approach, but here we have the need to use the second parameter. We can't leave it out, and in the int array we can leave it out. The int array is the same thing. We can write it here, or we can leave this 0 out. A little speciality of this class. So it's a derived class, and the superclass is array with the template type integer you have seen. And if I have a size 0, we get this out. This is the outcome if we create an int array of size 0. If we write it like this or like that, both is possible. Or maybe the faster function int array of is is really good so far. It creates inside, it creates int array, and with a 0 size, or maybe if we want to have some elements, it creates int array with 3 elements and gives us this int array back. So at the end we always have the class array with the template type inside and with these elements set up. So this creates everything from itself in this method here. Okay, next. Strings are indexable like array, so we can use it too and print it with a for each. We could have a string like mobile computing, string str does have this for each like the array 2, and we can print everything out, make a print line afterwards. And we get the string. To make it a little bit wider, I make a space after each letter, and then we get printed it out a little bit more spaced there. Now, okay, we can change maybe any value string on the position 3 is then E. Moment. Though this won't work. Okay, this won't work, but it is indexed. We have index access. You see this, and I thought we can have a value out of the string. Yeah, we can read it, but we can't write it, actually. But we can read it. So it's the same as I would write a for loop for I in 0 until the length of the string. I could print str from position I. And better to do a print line in between, having it on a line itself. You see, this is index access is possible for strings, but only readable, not writable. We can't rewrite it. You cannot rewrite it. The set method is missing. There is a get method for strings defined, but the set method is not accessible or not defined for the string. This is why we cannot access it with this index operator. Okay, what else do we have? We have raw format strings with 3 times double quotes. Raw format strings have 3 times double quotes in front as prefix and at the end as trailer or postfix. And this is now a raw string. In a raw string, those backslash escapes aren't recognized, so we could write \r \n and still get the string in one line, and we see this \r \n thing while writing it. You see, it's automatically it is not parsed while creating this string. So if the compiler creates a string out of this notation here, the compiler does recognize this is a raw string, and if we write here a backslash, then this backslash will be or the backslash, and this R will be the R, and so on. If we do not use it, you know what you have to do. If we have just normal strings and we want to have this backslash escape not escaped, we must escape the backslash, and then we get the same outcome. More critical, you see this, is it if I take a path from the operating system Microsoft Windows. So in this path we have lots of backslashes. I have to escape every backslash. C double dot double slash is giving me 4 slashes. Then we have a directory maybe called Windows, and then system, and so on. Yeah, and that's this is the normal way to write it. And if we we see this here, you can click it in the IntelliJ, it is highlighted, so we could click it now. But if I use a raw string, make a raw string, now we get all those backslashes, and that's why we could leave them out. And it's better to read now. Like this. Yeah, I thought it was, I don't know, I'm not sure so far. I thought it was a double. Yeah, okay. Questions so far for this? Template replacement, I should make an example for this one here. For template replacement, we could do something like a string, give something out. What will we do? Member number, something. We have a array. Let's make another array. Members is int array of, and then we have 1, 2, 3, 4, 5 members in our array. We can write simply this one. This case, you know already, is really simple. We have member number 1. Maybe do it with the print line here. Member number 1, member number 2, 3, 4, 5, and now we can also produce some code inside this. Member number are it plus 100, and this code will be evaluated, and the outcome, the return value of this expression, is then placed in the string. Here we could also call functions in this, or produce complete code. So this is something similar to a lambda function body. We can write quite everything in here, and the last statement is the return value. Yeah. If we have more complex things that produces code here, we could write as well if it is smaller than 3. So the first 2 members have this condition fulfilled. We could write it, else we write it plus 100, and now we get the first 2 members have 1 and 2, and the others have the 100 added. And this works because of the if-else conditional expression is returning a value. For returning the value, it is needed that this case and that case, the alternative case, both are exist, and both return the same type. The compiler will recognize that and would warn if it is not like this. So if we add this one to it, oh, it does recognize it. Okay, let's see. Yes, okay, he's doing it, but we need both. We need both paths, so the conditional expression and the alternative are both needed. Okay, I think it is recognized because at the end there will be a string made out of this. Other approach, I could write this in a function giving the value back. Let's make a small function, member number, giving us a value. Num is integer and returning this expression. And I don't call it num, I call it, and then we have this here. And now what does he say? We have to give a return type. The return type is int, and this is the case. We now have a return type called integer, and if I change this to double here, the return type is not the same of the alternative. The else path is not the same like the return type of the conditional if path here, and therefore the compiler says this is not possible to do for me. So you want me to give a integer value back, but in this alternative path there a double value is produced out of the sum of an int and a double value, and here we have a integer value. Please resolve this problem. So we could resolve this problem in two cases. First case could be, okay, we say we make here double. Now the problem is this way, but we can say here 2 double and everything is fine. Or we do the other way. We say we need the integer, and then we could make a integer out of this. And this should be the solution which is automatically done if we put this expression down here. You see, if this expression which makes a which is mentioned by the compiler, it is not working, it will not compile, will compile if we do it here. And the only thing there is, this is automatically evaluated or automatically casted to the desired value, which is in fact, or at the end, it is a string. So this, the compiler knows I want to have a string as the outcome of this expression, and there is a function which returns in fact a string out of this. And then this outcome or this outcome, whether it is, must be cast to a string. This is why we take this outcome and say as to string. And now you see the problem is away. The problem is gone away. This is a int value, this is a double value, but both values are able to be cast to a string or to produce a string, and that's why it will not be a fault to write this down here. Okay, so member number is now the same solution as if we do this if with this else path directly in here.
Professor, can we use any type?
You mean any object type or any primitive type? You can use any primitive type for sure, and I think you can use any object type too, because if I use a object here, every object can be cast to a string. This is the same as Java does it. In Java we can make a string out of every object, because the object class, the base class of every class, has a method to string. And as I mentioned at the beginning, the integer type has a capital letter in front, and the double type as well. That's why the integer value is a object value, and every object value has a method to string. So there are only objects in Kotlin. We say goodbye to primitive types. So our primitive values are objects as well, and so far they have a method to string. And this is why everything what comes out of this if, regardless which type it is, we can use a toString. But if we change type and say it is integer, then we have seen it is not automatically done. So the type conversion is not automatically done. But this toString approach here is working fine.
Thank you.
You're welcome. So I hope I could answer your question so far. If you feel free to ask. So if you have any questions, please feel free to ask. We can do examples, lots of examples. Good. This is the template replacement, and you will see what is done. We take this expression, make those braces around, and say toString, and then it is not needed to have the same data type in this parts. Okay, good. That were those basics. The last slide to the basics is belonging to the packets. If you program Java, you see it here. We have normally the Java lang sub-packages, or the classes in the package Java lang usable. The same thing here in Kotlin. We have the Java lang packages available in Kotlin 2. We do not need to have a import for the Java language, and as well as for the Kotlin JVM package is a special package which makes Kotlin compatible with the Java virtual machine. There are things inside and other packages from the Kotlin standard which are available in every variant of Kotlin, regardless if you produce code for the JVM or for the JavaScript or for a native. You have always the basic Kotlin packages available, which is Kotlin.star. So all classes in the outermost level, in the upper levels, and then in the sub packages there are annotations loaded, collections loaded, comparisons loaded, IO packages loaded, ranges are available, sequences is a package, and the text is a package which is loaded as well. Without import we can access lots of classes and extension functions which are defined in those packages here. And if we produce code for the JVM, we have the Java language package available, so we can problemless use everything we know from Java in the Java language. And additionally we have Kotlin JVM packages which make it easier for us to access some things in Java. Okay. Another thing in case of packages is maybe you know some conflicts in if we have in Java several classes with the same name in different packages, which is possible, so every package is a namespace. and therefore we can define in every package in Java the classes again. So maybe we have two classes called math. We have a own math class with some special solutions for maybe how to calculate the square root or how to calculate a sinus value or something else. Maybe how to calculate the power value of a integer number with a very fast algorithm, and we want to use those math expressions. In Java we had to decide, okay, I can take only the math class from the Java lang because Java lang math is automatically imported. I don't need to write the import statement, and if I would write my import statement to import my package math class, I can't access the Java lang math package because there's only one math class in the JVM known. It must be unique, the class name. If we use it with the import, the class names must be unique. If we have if we have different packages with the same class and we want to use both in our code in the same file, we would have to proceed. We could only import one of those classes with the import statement in Java, and the other class we had to proceed with a full qualified package name, and then we can use both classes in our code. So in general, if we never use any import, we can access every class if we just always write preceding package, full qualified package name preceding the class. We can access the class. So if I want to have Java lang math, I can always write java.lang.math, you know. To make it easier, I write this import statement and say I want to have this imported, and then I can access it with only the class name. Yeah, and here in Kotlin we have the possibility to say import me this class or this package as import me this class as this alias, and then I can access only this class with that name. And now we have access to both classes called math. We have the Java lang math and we have our own math class in our own package. And now we can use both without preceding the full qualified package name. And that's all. This is just some syntactic sugar. The old solution to precede every access to a class with a full qualified package name exists. Yeah, still exists. So if we want to, if we like it, we can write this. But I think nobody likes to write so many full qualified package names, because this could be, if it is twice on one statement, in one statement, if it is twice there, it could be half of the line, or maybe half of the size of your window of your screen maybe. So we want to write shorter names, and that's why this is a really nice abbreviation to make this access here unique and short. I think it is simple to understand it, what it means. Good. So far, this were the basics, and now we can. Oh no, we have one last slide. But we can go over very fast, because we know this if-else statement. We had it several times, and it returns a value, and the return value is the last instruction in a block. So this is a outside of any function, which is defined with this fun statement. Outside of the functions. In the functions, if I want to return something in a function, I have to write return. You see, this is wrong. So we need the return statement to say this is the value I want to return. But in all these other things, in this lambda expression, I can return a value, and the return value is always the last expression in a block. The same thing for the if. So if true, then I can do things. Maybe value k is 5, and I return k plus 3. In this case and in the other case else, but this case is not needed, and maybe the compiler is so clever and finds it out, but he doesn't. But he just writes a gray line under this true, so he just says, hey, never, why do you write such a thing of code? Because you can remove this if. But this is a thing the IntelliJ IDEA is parsing out. Okay, well, okay, R is 6, and we return R minus 2. In the other statement part, in the else part, and the last statement in a block is the return value. Now we have a return value here in this if part and a return value in the else part, and we can print it. So we get 8, and 8 is 5 plus 3 because the if is true. If we have false, we get the other thing printed. This is automatically the return value. Return value is the last statement in a block, and we do not. It is not allowed to write return here because this is not a function. A return is not allowed in this if. You see, function main, we could go out of the function main if we write return somewhere, but not in this if block, because the rule is the last statement is returned if I use it as a return value. So if I use it as print line maybe, or if I use it in a variable, a value m is this return value. If I don't use the return value, the if and else is still the same as it was always, as it always has been. But now we can use it as return. Yeah. And this is the last statement in a block. So if I miss this, then that is the return value. I can write code like this, maybe. And you know, you don't need curly braces here around. And then you can make a typecast or something similar to a typecast from a Boolean value. So if, and this can be used in another if. If is 1, maybe make some braces around. This way we give back true, else false. It's really a statement which not makes sense, but it is possible to do so. The first condition is making out of the Boolean value false, the integer value 0. If the Boolean value is true, we get a 1. If this statement produces a 1 out of the Boolean value, we return the true, else we return the false. So if we do a Boolean b inside and we say our b is something like 3 is smaller than 5, then we get m, and m is true because 3 is smaller than 5. Oh, no, my m is false, so let's see. If b is true, if b is true, we have 0 now. That's right. If b is true, we have 0, and 0 is not 1, so we get false. So we get not this statement. This is the function not. Implements some kind of not B. But nobody would write it like that. Yeah, nobody would write this. It's just to say, okay, here comes a value, there comes a value, and we can combine it. Have you any questions? So, switch and when expression, we have a case distinction, and this is the when expression. I have already shown it to you, but one example we were missing. I said, okay, we can use the when expression when a value k is maybe 0, and I can say when k is 0, do this one, do maybe 5, else do -1. That's the same as the if statement. I can print it out. It has a return value, and the return value is the case matched. So I need the else path. The same reason is for the if. It must be for the compiler. It must be evaluatable in every case. This k can be. If it is null, we get 5, but if it is not null, if it is anything else than null, we have to get a value because we return this value. In every case, we have to return a value here, and therefore we need this else path. If I take it out, it is an error, but only if I use this in a other statement. If I use the return value. If I do not use the return value, this is not a fault. Only if I use the return value, this will be a fault. The same thing as with this if-else. So now we have k is 0, and if k is 0, we print 5. If k is not 0, so if k is 5, we get the other value back. We get the -1 back instead. This was the one thing. We can switch to types. If we want to switch to types, if we say if it is int, then we put out 10. If k is an int, we put out 10. So now we have the problem: k is an int and k is 5. K is 0. Sorry, k is 0 and k is an int. We have two cases match. What does this when do? This when can only get out one value, and this is the first case which is matched. So we can say if it is an int, we get the 10, and if we change the order, we get out 5. Yeah, you see this little difference. If we mix the switch case with type test and with value check, then there could be several conditions match this variable. This variable can be an int and can have the value 0, but we have only one case which is affordable. And we can combine it with 0 and 1. So if I do it is 1, we get the 5 as well. Could be 0 or could be 1 now. Can have several values, and we can say if it is 3 and is an int or is an int, we go in there. So if it is 3 or is an int, we go in there. But I cannot write 1, 2, 3 here. Or can I? Yes, I can. Okay, you can have the 3 here again, but the first match is the match which is done. It still may be an int, so we still get the 10. Value is 1. Normally the case with the one letter here is with the number 1 is afforded or is used, and we should get the 5. But since k is an integer number and we test here on the integer, this will be true, and that's why we get the 10. This condition is first condition which evaluates to true, and that's why we get the 10. Okay, when we take this back, we have 3 here and we have 3 here. We can have it several times, and the first one is done. So you know, if we use switch case in Java, maybe it is not allowed to have several cases with the same value. It's not allowed because the compiler says no, there may never be 2 cases with the same case label because it must be unique. But here it is not like that. So this case will be done, and there is no not the possibility to say go in here and go forward and give this value, give that value, and do this one. We just we simply have the break after this case. So a switch case without a break is not possible with this when statement here. Good. We can do another thing with the is check. Is int give the letter I, is double give the letter go there. Okay. So is double give the letter D, otherwise give a question mark maybe. So now the compiler recognizes that k is int, and therefore he says it isn't, this is a int, and you may not check it against a double because it can never. This makes no sense. Yeah, if we say this is a any type or a object, because we only have objects. Good. Object can't be object, can be any type, I think. Yeah, it can be any type. This is the object type in Java is the object from Java lang, and a primitive value never is a object in Java, but in Kotlin we need something above the object to include, and this is where we talk about today as well. We include the primitive types into the hierarchy of objects, and they are included into the object hierarchy at a very top level. So on the level where we have the base class object in Java, on this level we have the primitive types included into our object tree, into our class hierarchy, and this is a class above the object class, and in this class any, under this class any, we also have the primitive types. So a primitive value number 3 is a derived class from the base class any. This is called any type of object, and number 3 is an int, and everything is any type of objects in Kotlin. So this 3 is also a object of type any, and that's why if I test in my when statement the object type of any, I can test it on the derived, on the special class int. So if this is maybe an int, then print I. If it is in double, then print D. If it is an object, then print object. Oh, so okay, it will not go. We could print O. So I give back the same data type here as well. It's the same reason, because I want to print it. And we get I because it's a number, and if we say it's an object, then we get back object. So if it's an object, we get back O. Really nice, I think. And if it's a double, we get the double. Good so far, and if we do it here in the string expression evaluation, maybe we can say the same as before when we did it with the if else. Then we maybe can say, in this case, I want to return a string, and now this will work. Now it is clear that this expression here is the return value of this expression here, and that is something like a function, a functional expression or a lambda, and therefore this here is casted to string, or the method to string is used, and that's why this character and this character constant here is made as a string, and this string is made as a string as well, and therefore I can have character constants here and a mixed approach here a string. If I leave this expression is evaluated and can be used as a assignment, or can be used as a return value of a function, or can be used as parameter for print line, and therefore every outcome must be of the same type. Okay? I hope you understand what I want to say with this. So the better solution would be like that, but if we use it directly in this string expression here, in this template expression, then we can change the type. It's amazing. Good, so far. This was the example I've been missing, or you've maybe been missing because it did not work in last week. I did not change to the anytype, but if we change to the anytype, which is base level of all classes, we can include the primitive types into the anytype, and then we can do is-checks with all classes. That's the reason why it didn't work last week for me. So loops, I think we do not have to talk more about loops. Loops are known. We have for loop, while loop, and do while, and in the example at the beginning of the lesson today, I have shown two more methods to get loops running, counting loops. This is the repeat statement. Here again, repeat statement. We give in a number 10 times, and we give in a lambda expression body. If we want to have 10 times 0, then this repeats 10 times 0, but it does not do anything, so we should do anything in here. What do we want to have to repeat 10 times? Go back. If we do this repeat, let's look if it gives something back. And it gives a unit type back. Today we talk about this unit 2. This is something like void. It does not give anything back. So if we want to repeat something 10 times, we have to say, what is this 10 times? We could print 10 times 0 on one line. Then we would write it like this. This is a counting loop. The 10 times, and if we want to have the counting, the index number, which is the counter for the counting loop, and then we get this one, and it is starting with 1 as we expect and ending with 9 as expected too. So maybe I think there is a function times, but it's in the array. If we make the array again, let's do a small array of int 1 2 3 4 5. Very simple. Then we can have array times. No, it is not done with the array times. This was the repeat approach. We can have for each here, and then we give an action which is done with each element. there is as well for each index. We have two parameters, and in the easiest way we have only one parameter, and it's called it. So both approaches here, up here and up here, are similar. We can do times print and take array of it. Not repeat 10 times, repeat times array size. Both loops are now identical. This is what we have additionally here, but the basics for loop, while and do while we can form or describe as well. So jump expressions or jump statements. We have jump statements and we know the return statement. This is only possible to do in function bodies or lambda expressions, and we have a break. This is normally used in loops, and a continue. This it's not normal. It's only used in loops. We can break a loop or we can continue the next round with this jump here. Okay, the next is breaking or continuing with the label. We can use labels, and in Java 2, so we have loops which are nested or nested loops. Let's make a nested loop. So normally nested loops are done with multi-dimensional arrays, maybe a matrix, but this is a thing which is not really nice solved in Kotlin. So if we want to have a two-dimensional array, maybe of the values 1, 2, 3, and 4, in one line 1 and 2, and in the next line 3 and 4, we had to create a array of arrays, array of int array, and we should put into this array of int array two int arrays, not array of just array. We want to create a array of two int arrays, and the int arrays have both. The first one has 1 and 2, and the second has 3 and 4. So now we have a little problem. We must create two int arrays with two values, and then we need a loop to introduce the values, because we could set them null or we could set them to 1, 2, but we cannot set them all to distinct values 1, 2, 3, 4. That's why we need a loop now. So we need a loop array for each, and then we have or array for each index in this way to access the array with the index, or we make a nested loop. Let's say I starts or is null, not is in null to array size, and in this inside we go from j in 0 to array from I size, and then we can have the values in this array I and j set to I plus j. Then we get 0, 1, 2, and I plus j plus 1 gives us 1, 2, 3, and I plus j is not right, because we have 1, 0, then we get a 2, and we have 0, 1, then we get a 2 as well. So we should have a number starting with 1, and then we can just write n plus plus. No, this is we can't write can we write? Yeah, we can write n++. We are lucky we can write n++. Now we can access our array of arrays and try to use this for each. In here I have it, and it is a array, so I can go to it for each and say now print it, and after this loop make a print line. And then I have this nested loop both with this for each approach to print it out again. Until should use until. And then we have 1, 2, 3, 4. If I print it with a space in between, I would do like that. You see, it's not so nice, because now in the older languages it is more easy to write down an array. So if you know Java, we can write int array A is this kind of array, but this is not more. This is not, so this kind of array initialization is not possible. That's now the Kotlin way, and this was the old way. This is one thing some developers mention as it is not nice. This is the only thing they have found out which is not nice for them, because they like to use arrays. But Kotlin says, why are you using native arrays? We have better things. We use collections like mutable lists or use lists or use maps and use objects, and don't use arrays. That's why it is maybe not needed to go in multi-dimensional arrays. It is possible, but you see, it is not that easy. We just we should think about go away from arrays, go to lists of objects. What else? Yeah, we would jump out. We want to jump out this loop. So we can do it with a label. We can leave in the inner loop if I say if it is bigger than 0, or if it's bigger than 1. We can say break, or we could say continue as well. So we break, but this is not possible because this is a lambda expression we could return. This is a lambda, and we can only leave this lambda with a return. It is a method body, and it's not a normal function. In this normal function we could use it. So here we have to use return, and if I do the same thing again with nested loops in this basic variant here, we can have it like that. I print a, I, and j, and therefore I can't use dollar, because with this dollar I just reach the name of this variable. But to access the array indices, I need. Now we have it, and for the print line at the end of the inner loop, I have to use curly braces again. Now we have the same outcome, 1, 2, 3, 4, but here in this inner loop I can now use a break to break the inner loop. If my array on position I and int j is bigger than 1, I could break. A loop is breakable. A function is not breakable. A function is just returnable. This is the only jump allowed in a function body, and in a loop we can have a break or a continue. But, and this is new, if we want to break both loops, this is not new. You know it from Java. In Java we would say this is my break label, this is the outer loop, and we write it like this. But it's not allowed in Kotlin because this colon is the type. I could write here array of int array. This colon is the separator between a variable declaration, or is part of this variable declaration. It's the separator between the variable name and the data type. This data type is here not needed because we can derive the type of from the right side. This is what Kotlin does. We derive the type, so we do not ever always have to write this. If we write functions which return values, we have to define a type, but for the compiler to check if the returned value is of the desired type, that's therefore we have to write it down here. But here we have no need to do this because this has any type, and this type is set for this value afterwards. In functions we need it because there could be more than one return value or more than one path which returns a value, and if so, the compiler can check if every path in this function returns the same value of the returns a value in the same data type. Therefore we have to give the data type, but not here. Okay, and this colon is used for the data type, and the new thing is we make at. You know, if we make the at in front of this, then it is a annotation at, how to say, at annotatable. There's several annotations possible. There we could write some annotations here, a delegate or what else. And if we want to have a case, a break, a label for a break or case, a label for a break or a continue, to break or continue a loop, we have to mark this loop with the label. If we want to have this outer loop marked, we just write the at sign at the end. Now we can say outer at break. So this is what here written up, or break at outer. This is then the solution here. If we want to break both, we have break at outer, and I think we can do this with the, so you see 1, 2, and then it's finished. We break both loops, and here we have the return, and the return goes back out of the array. Let's say it without the outer. What happens without the outer? We just break the inner loop, and we get 1, 2, 3, and then it is away. And in the second time we always go out. So this return goes out of everything. If we want this return not to go out of everything, I think we could label the inner, and we return just the inner. Oh no, this is not allowed. I remove redundant inner. Okay, redundant inner, return outer. Let's say return. Redundant. I think he can return to a label 2. But I have never used it, so it will be the first example I'm writing. In this approach, we have loops nested. This is a case of nested loop, like this one. Here it is similar. Here it is simple. We can break and go out of this loop. It is marked. Here we have lambda expressions, which also form counted loops. And we can't break, we can only return. And where does this return go? Yeah, this return now goes out, because if it is the same outcome like break with the outer loop. And I thought it is possible to say just return the inner function and go on with the outer function. But I think it is. I think it is. Um, but if so, the inner loop would have to go to the number 3 as well and not stop after number 2. So you see there is a difference. Here we can use the label, and here I thought the label is possible as well. Returns, break and continue, and I think we have something like return label name. Return, but we must annotate, we must give a label somewhere to say where to return. Okay. Have you any questions for? Normally you should not program like this. This is not really easy to read, because anywhere in the nested loop you break this loop and go on with this loop, or break this loop and stop everything. And if we have 3 or 4 loops nested, I don't know is this really needed to nest so many loops. So maybe you should think about, can this be a little bit easier, because the complexity is multiplied. We have complexity linear n, and we have complexity n again, so this is n squared in complexity, and for every loop nested inside the other loop we get another exponent, a higher exponent in our complexity expression. And if we have 3 loops nested, we have n times n to the power of 3, and therefore it is not more solvable for big numbers. It is too complex. This is the border. It is n squared, so this can be solved in most cases for big numbers as well, but it's the border case here for the complexity. So these were the basics, and now in the last 15 minutes we jump into classes which will be the theme we talk about in the next weeks. Now we go into the object-oriented solutions, and let's have a look at classes. It's really funny what Kotlin does for object-oriented programming. Class declarations are very simple, more simple than you know from maybe C++ or maybe Java. If a class has no body, it can be omitted. A class has not more the need to have a body. I can take this out, we don't need it anymore, and we go on make new examples. So let's write a first class. The first class could be class A. Value from this class, I just write this expression, and we can see this is a object of type A. So it's just a new type and it's empty. Define a new empty class. Create a object of this class, of class A, and print it out. So we see main to KT. We say we know this from Java. Maybe this is the class name, because we are on a Java virtual machine, and therefore we always need a class. Every main method must be part of a class, and that's why Kotlin is creating a class named like this file. It makes out of this file name main to KT, it makes a Java class with a capital letter main with a big M, and then appends the KT for this is a class coming from Kotlin compiler. It's a Kotlin class, and in this class there will be a function main. This is this public static void main. Java needs to run code, byte code on its virtual machine, and therefore we have in this the main function, and in this main function we define a class called A. So this is a class defined in class main KT in the static main function, and there it is a inner class, and this class is referenced, or a object is built, and this is the object hash code for that, which says we have a reference to a object of type A. If we put it out of this main function, like we would do maybe in Java, then we get just the A. So this A isn't out of the function, it is upper level. It is not one level higher, so outside in the class main 2, so it is standalone, and now it is nested. But nested in this function, and this function is part of a class called main2kt. Okay, we could do it here as well. So we don't need the function body, but we can append one. In Java it would look like this. This would be the Java approach, but why, if we do not write something here, why we should write those curly braces? It's the same thing, no? But we can leave it out. This is the first thing. So just to define a new type, and sometimes we only want to have a new type. And maybe we want to have a new type derived from another type. So maybe I should actually look how we do the extension. I think we have to use this, and we must do it like that also, something like that. But maybe it's not derivable. This is not derivable. What does the helper say if I want to derive this type from that one? It's easy to do this. It is the derivation, but yeah, okay, now it is. Now it works. So we have a alias. We import the Kotlin integer as integer 1, and we can derive from this integer 1, and then it is possible to do this here. But now we have 2 more errors. The type is final, so we cannot inherit from this type because it's final. That's the reason. But it would be inheritance from this type. But the type is final, inheritance is not allowed. You know this keyword final for classes in Java. If I want to permit subclassing from my classes, I make the class final, and then nobody is allowed to subclass my classes. That's why this example with I derive from int and make this int another name is not possible. But if I want, you have seen what this IntelliJ program has done. If I want to have an alias to a class, I can say import Kotlin int as I, and then I can use ice. This is, I think, really simple. Well, I is 3, and then I print I. Also cool stuff. We can just build alias for a type, so we do not have to inherit and make it over inheritance to make a new type name, which is the same as the super type. We can just write it like this and have an alias, and then this type is used as the same as it would be that. So this is an empty, like an empty class derived from integer, and it's nearly the same. Okay. Good. First thing, we can omit these the class body. Constructors use the keyword constructor. So you know Java or other languages where the constructor is having the same name like the class. This was the approach in other languages, but here we have a keyword is called constructor, and the constructor is the method name. So we replace a method with an which formerly had the name of the class with the new keyword constructor to say this method is a constructor. So constructor is actually the method name. Let's try to do this here. Have a class A. I put it away, this integer again. So we want to have a class A, and we want to have a constructor here, and in this constructor we don't want to have any parameters, so we just write A and maybe print now I get this A constructed A's. This is a constructor. And you see the difference. We don't need to write A, just write constructor. So Kotlin makes a difference between, oh, we have just 1 minute left. Maybe we stop here in this moment. It's just 1 minute, it's in some seconds left. Maybe we stop here and the rest we do tomorrow. You have an example down here, so maybe in short, this is a primary constructor and this here is a secondary constructor. A primary constructor may be written directly after the class name, so this is typically that what it was before. We have a class name, and after the class name we make a list, a parameter list, and this is the beginning of my constructor. But what comes after, the thing which comes after this primary constructor is the class's body, not the function body. This constructor here, primary, is just doing what simple constructors do, take some values as parameters and set them on the same named attributes. But let's talk about more of this. We've gone through all the basics and we go into object-oriented programming, and that's what makes the bigger fun. So for now, we make a break, 15 minutes break, and we start over in 11:30 with the Android. Okay? So stay tuned.
Okay, Professor.